Hi, this is Mrs. Cribb, and I'm going to start off this video just reminding you about specific heat. I wrote the formula right here for specific heat again. Q, which is in joules, right here it's in joules. Q is equal to M for mass, and mass is in grams. C is that specific heat value you get from a chart. MC and the delta T, and remember that delta T is the change in temperature, and that's the final temperature minus the initial temperature. Okay, now we talked about that, but one thing I want to make sure I pointed out is that the rates of cooling, this portion right here, are also related. If you have a high specific heat, that means your C is a big number, then it's going to take a long time for it to cool off. So specific heat means it takes a lot of energy to get it warm, and it takes a lot of time for that energy to get in, so it also takes a lot of time for it to get cold. And I'm going to draw a warming curve of some substances with high specific heat and some with low specific heat. It says if the temperature rises quickly with the addition of heat, then the specific heat has to be low. And it means a small amount of heat results in a large change in temperature. A gentle slope, which means a really easy to go up slope on a warming curve, means a high specific heat. So I'm going to draw a few pictures, and I think I'm going to use this space right up here where I had left a big old blank for the latent heat to draw these two warming curves. So first I'm going to draw one that has a high specific heat. And that means it takes, a high specific means it takes a lot of energy. A lot of energy for the temperature to go up. So we have a graph like this, and on this side is the temperature, so it's going to be Celsius, and this is going to be the energy that I'm adding. And remember, energy is going to be in joules. And so if it's this high specific heat, that means it takes a lot of joules, a lot of energy to be added before the temperature goes up. So I add all this energy in, and the temperature slowly rises. Okay? And let's make it longer. It slowly rises, and then it gets to the point where it goes flat, that lazy latent heat. And then it'll slowly rise again. So you see a very gentle slope. It's kind of takes a lot of energy to make the change, to go from one temperature to the other temperature. So this is what happens with a high specific heat. So if it takes a lot of energy and a lot of time to warm up, it takes a lot of energy to lose, a lot of time to lose all that energy. So the slower it heats up, the slower it cools down. The slower it heats up, the more energy I'm having to add. I'm having a high amount of energy, makes a slow amount of time to heat up. Now what if it has a low specific heat? A low specific heat, a lower value. When we draw that one, well, low specific heat means the temperature here and the energy is down here. A low specific heat means I only add a little bit of energy and the temperature goes way up really fast. And then it has that latent, lazy time when it changes spaces, and then it goes straight up again. Well, not straight, but really close to straight up. Let me draw that a little bit better for you. It goes up like quickly, and then a lazy heat. So if it only takes a small amount of energy, it has a low specific heat, and the temperature rises quickly. Well, if the temperature can rise quickly, it can also go down quickly, cool off quickly, because I can lose that tiny little bit of energy quickly. So again, high specific heat means it takes a lot of energy to heat up and a long time to cool back down. Low specific heat means it takes a little bit of energy to heat up and a little bit of time to cool back down. So keep those in mind. That has to do with this portion of the notes right down here. Now we did these two problems already. And so what now I'm going to do is the complex thermodynamic problem I've covered in a different video, and I've already put that out there for you to watch separately. It's a little bit complex of a process, and the one I did on the video was different than the one I did right here. So just follow along the one I did on the video. I think the temperature changes and the amount are slightly different. So now we're going to go to cover the enthalpy, or the heat of reaction. The change of enthalpy, the change of enthalpy that occurs during a reaction is called the enthalpy of the reaction. Okay, and the enthalpy of the reaction will just be the delta H. And the formula for the delta H, or the change in the enthalpy, is just the heat of the products minus the heat of the reactants. And you can still kind of think of this as the second thing minus the first thing, because you know in a reaction you have reactants and they do something and they go over to the other side and they cause products. Well, the products are the second thing, and this is what you started off, the first thing. So all changes are the second thing minus the first thing. And then, so the change in enthalpy, or change in the heat, is the heat of the products minus the heat of the reactants. So let's look at this equation right here. We have 2 moles of water. Remember, 2 moles of hydrogen. Hydrogen is diatomic. Plus 1 mole of oxygen gives you 2 moles of water and some kilojoules of energy. Now, a chemical reagent, it says one such as this shows that the reactants, products, and it shows you the amount of energy that was released or absorbed, and as heat. And this is called a thermochemical equation because it adds in the heat. Now, in this case, you'll see the heat right here. This is the amount of energy that is produced, because see, this is this whole side is the product side. So that means the heat is produced. If you produce heat, that means you're creating it. This is an exothermic reaction. Exothermic, because the heat is made. You could feel this heat coming out of it. You could feel the heat leaving. It would create heat to you. Okay? Now, I'm going to draw exothermic reaction warming curve. These have negative values for delta H. Negative values for delta H. Okay, so let me put that reaction that we just had back up there. I'm going to draw it again. Let's see. This is an example reaction. 2 moles of hydrogen gas, and it's going to be important you put all the phases they're in this time, plus oxygen gas yields 2 moles of water in a liquid state, plus 571.6 kilojoules of energy. Okay, so what would the warming curve look like? Well, warming curves are always going to be, in this case, it's going to be kind of energy on one side, and so on this over here, we're putting the energy content. How much energy does it have? Energy content on the x-axis, okay? And the energy content is usually in joules or kilojoules. And then this is going to be basically time. As time goes by, what happens? Well, in this, it's an exothermic. It has negative values. So delta H, which is the H of the products minus the H of the reactants, okay? What we're going to do is we're going to start off with reactants that are up high, because the reactants start first. And the reaction's going to happen, and then we're going to have products down here. Now, this is not a complete warming curve. You've watched some videos where they have the activation energy, where it goes kind of like this. And we're going to cover all that soon. But you're still only comparing the beginning, where the reactants are, to the ending, where the products are. You're just comparing this height to this height there. The difference between those. So this is where the reactants would sit, and this is the amount of energy that the reactants would have, where my dot is. And now this down here is at the end where you have the products, and this is the amount of energy the products would have. Now, it doesn't matter what they are, because the change in the heat is the products minus the reactants. Well, notice that the value of the products, let's give it we're going to count up. Let's make this 10 joules. 10, 20, 30, 40 joules, 50. There you go. I put some numbers up there. Okay, so in that case, the reactants would start off with 40 joules of energy, and the products, we go across, reads it with 10 joules of energy. Well, notice that if I calculate the delta H, it's going to be the products, there they are, products 10 joules, minus the reactants, 40 joules. 10 minus 40 is 30 joules of energy, but negative 30. Negative 30. See, it's a negative value, negative. So when you have an exothermic reaction, your delta H, your change in heat, is going to be always a negative number. The products are always going to be less than the reactants. So when you do products, a small number minus a bigger number, you're always going to get a negative value. So exothermic reactions always have the products lower than the reactants. Now what about, now make sure you put all these things in your notes, okay? What about the endothermic reaction? Okay, so I need to find an endothermic, here we go, here's a reaction. We have 6 moles of carbon, a solid, plus 3 moles of hydrogen gas, plus 49.1 kilojoules yields C6H6 liquid, which is benzene. All right, this, in endothermic reaction, the warming curve, you always have a positive value for delta H. Endothermic, the heat has to go in. Now notice, here is the heat. The heat is in joules or kilojoules. It's on the reactant side this time. That's the reactant side. That means it's like pouring it in. You treat the heat just like I'm putting an ingredient into something. So I pour it into the reaction vessel, and I create C6H6. So C6H6 is made out of all these things. That means this heat energy is inside there. I had to suck it up to make this product. So the warming curve for an endothermic reaction, we start off with, again over here we're having energy content, okay? And this energy content in joules. We start off with the reactants down here, and maybe that's 10 joules, joules. And then the products are up here. And so that's the product side and the reactant side. Remember, the reactant side comes first. Well, maybe the products now up here are 50 joules, because that's higher. All right, so if I wanted to calculate the delta H, it would be the heat of the products minus the heat of the reactants. So in this case, it would be 50 joules minus 10 joules, which gives me a positive 40 joules. So the delta H, the heat of an endothermic reaction, is always a positive value, and the products are always higher than the reactants. So look at the two warming curves. The products are lower than the reactants when you're losing that heat. The heat up here is lost or created, and it feels hot. This one feels hot because I'm losing all that energy. It's not inside the product anymore. It's not inside this. This water does not contain this energy. This energy, you can feel it, or take your temperature. Down here, the heat goes into it, so it feels cold, because all this energy that's inside, that's put into it, is sucked into the part of the molecule rather. There's a bunch of energy inside that molecule. That's an endothermic reaction. Okay, now reverse reactions have the same magnitude but different signs, and all that means is that up here, it's if you go forward, if you go from this side to this side, we have an endothermic reaction with a 49.1 kilojoules being sucked into it, being added, treating it just like a reactant. But if I go in the opposite direction of that reaction, I would lose 49.1 kilojoules. Okay? So if I go forward, that's the forward reaction, I'm going to put 49.1 kilojoules in. But if I go in the reverse direction, I'm going to lose 49.1 kilojoules, because that amount of kilojoules has to be taken back out so I get just those things. So that's what it means by the same magnitude but different. And we're going to talk about reversible reactions in more detail later on. All right, next we have the enthalpy heat of formation, delta H sub F. So you've had the delta H of fusion, and that's turning something from a solid to a liquid. you've had the delta H of vaporization, and that's turning something from a liquid to a gas. And you've had the delta H of the reaction, that's just the heat of the reaction, and delta H now of formation. And that's just how much energy. It says the change in enthalpy, heat, that occurs when 1 mole of compound is formed. So formation and formed from its elements. The delta H of formation for elements is 0. Why? Because they're already formed. I don't have to make them. They're already there. So I wouldn't have to worry about calculating the delta H of formation for this one. So what I've done here is I went ahead and wrote an example equation for you. Now you'll notice we're using half a mole of this, and that's because the delta H of formation says 1 mole. I want to know how much energy, what change in energy happens when I create only 1 mole. So I had to fix it so I'm creating only 1 mole of water. You won't have to worry about this, but what I want you to notice is if I have hydrogen and oxygen, I create 1 mole, right here, 1 mole of water. The delta H of formation is negative 285.8 kilojoules. Well, does that mean it's an endothermic or an exothermic reaction? Is the heat leaving or is the heat coming in? Well, if you go back up to our notes, a little bit farther up, exothermic, these have negative values. So this is an exothermic reaction. And so since it's exothermic, because the value is negative, how would I add it to this formula or this equation to make it a thermochemical equation? Exothermic negative values means it's on the product side. So you actually add it to the product side. That sounds weird because it's a negative value, but the negative value means it's leaving. So everything on this side is what's produced and what is leaving. Okay, this is the stuff that's made or leaving. The heat the heat leaves. Okay, if it's an endothermic, you put it on the other side. So up here, this was an endothermic reaction, and you notice that the heat value was written on the reactant side. So endothermic heat values are on the reactant side. Exothermic heat values are on the product side. All right, the amount of enthalpy in a substance varies with temperature and pressure, so these conditions can be specified. We have to talk about now what the standard state is, and it's defined as 25 degrees Celsius or 290 kelvins, because remember, to get to kelvins you have to add 273. It's 25 plus 273 is 298. All right, now what is the difference between standard state and the standard temperature and pressure? Well, standard temperature is 1 degree Celsius, but standard state is 25 degrees Celsius. I'm sorry, standard temperature is 0 degrees Celsius. So STP, right, the temperature would be 0 degrees Celsius and the pressure would be 1 atmosphere. We had to use those already. Well, standard state, really what it is you don't really walk around in the lab at 0 degrees Celsius doing your stuff. So the standard state is pretty much room temperature, when the temperature you'd be working in. So standard state is 25 degrees Celsius, and standard state is also 1 atmosphere, which is 760 torr. So standard temperature is 0 degrees Celsius. Standard state is 25 degrees Celsius. And now, we're also going to talk about the standard molar enthalpy of formation. And it's going to have this little degree symbol on it, delta H, F, and it has a little degree symbol up at the top. There it is. It's the enthalpy change that makes 1 mole of in its standard state from its elements in their standard states. So the little degree symbol stands for the standard state. Okay? All right. So now we're going to do example 13.3. And this is actually on page 333 of this textbook, this version of the textbook. And it says, what is the delta HF, the standard molar enthalpy of formation for this molecule, for this reaction? So we're talking about NO2. So this is another time when you're going to go and look up the delta H's of formation, the molar enthalpies of formation. So you're going to have a chart, and it's going to have molar enthalpies, oh wow, that was weird, of formation. And the one I'm looking at right now is actually on the same page, 333. And one of them is for NO2. An NO2 gas, and it's a gas here. I didn't write it in this formula, but it is a gas. You have to look at the state that it's in. The heat of formation for nitrogen dioxide is 33.2, and the unit is kilojoules per mole. What does that mean? It takes 33.2 kilojoules of energy for every 1 mole to create nitrogen dioxide. But if you want to know the heat of formation for this whole equation, well, we have 2 moles here instead of 1. So it says 2 times 33.2 kilojoules per mole. All right? And so that's a very simple math, 66.4 kilojoules. And that is how much, since we have 2 moles, I got to put the mole unit here. We have 2 moles, moles cancel. So the change in the heat of formation for this equation would be twice as many as this. 2 times that, 66.4 kilojoules. It's very easy. You just go look up the heats of formation for these guys, and you're going to use your reference charts for that. And then we have the heat of combustion, and I think that I'm going to cover heat of combustion in class. So we just want to cover heat of formation for now. Okay? All right. Hopefully this will help you, and I will see you soon.